Hello everyone. So welcome to this webinar on calculus part 1. So today we're going to do differentiation. And I assume that you are familiar with differentiation more or less today. So I won't be going through the basics. If you want to go through the basics, do watch one of my previous webinars. So today I'm going to focus on actually doing things effectively, and recognizing what needs to be done. And well, my favorite calculus meme, I'll Google it, XKCD differentiation, uh, creation versus integration. Here it is. And this is, in short, the difference between the two main things that we do in calculus. In calculus, we differentiate and we integrate. And differentiation is a very straightforward process. You only need 3 rules, which is the chain rule, the quotient rule, and the product rule. The power rule, well, power rule is x to the power n. So I don't use it as a separate rule, right? So an integration is infinitely harder. Okay, so just a quick reminder of the rules. So basic functions is that x to the power n, the derivative of x to the power n is n x to the power n minus 1. The derivative of sine x is cos x. The derivative of cos x is minus sine x. The derivative, what else do we need? E to the power x. The derivative of e to the power x is e to the power x. And do we need anything else today? Not really. Cos, sine, yes. Perfect. Okay. Now, if the function is replaced with something else, so for example, if you have not x to the power n, but more like a function to the power n, and that would be nf to the power n minus 1 multiplied by f dash, by the derivative of f. And the same here, sine f, if you have the sine, this is the chain rule. So cosine f multiplied by f dash, and the cosine f is going to be minus sine f times f dash, and e to the power f dash is e to the power f multiplied by f dash. Brilliant. Um, I should clarify what I mean by that. So this is just the chain rule. Yes, there's the chain rule. For example, if you have, instead of x to the power, let's say you have 3x squared plus 2 sine x to the power 7, and you want to find the derivative. Well, that's simply 7 multiplied by 3x squared plus 2 sine x to the power 6, and multiplied by the derivative of that thing. So the derivative of 3x squared plus 2 sine x dash, so that's 7, 3x squared plus 2 sine x to the power 6 multiplied by 6x plus 2 cos x. Lovely. So that's how you use this rule. Yes, f stands for a function where f is a function of x. So f is a function of x. It could be anything, right? So, and you can use that rule. So it's a very useful thing to remember, right? Of course, the reason why I'm writing it in this way because there's honestly no easy way of writing the chain rule that makes sense to a person who is not familiar with the chain rule already. The chain rule is usually written as d dy dx is dy du multiplied by du dx. Like honestly, this probably tells you nothing if you aren't already familiar with the chain rule. Or the chain rule can be written as like this. The derivative of f of g of x, the derivative of a composite function, is the derivative of f with respect to g multiplied by g dash x, which is also really unsettling. How to access the whiteboard. Here you go. Chain rule. The product rule. You might not be familiar with this product rule. If you have the product of two functions, u times v, and then that's going to be u dash v plus u v dash, and the quotient rule is u over v dash is u dash v minus u v dash over v squared. Let's do an example of the product rule. The example of a product rule is like this. So let's say you have x squared multiplied by sine x, and you want to find the derivative. So you find the derivative of x squared, so x squared dash multiplied by sine x plus x squared multiplied by sine x dash. And you can differentiate. So x squared is 2x sine x plus x squared cos x. If you have a quotient rule, let's say you have cos x divided by x cubed dash. So it's cos x dash multiplied by x cubed minus cos x multiplied by x cubed dash divided by x cubed squared, which is cos x dash is minus sine x multiplied by x cubed minus cosine x multiplied by 3x squared divided by x to the power 6. And of course you can simplify, so you can simplify like this. So it's minus x sine x minus 3 cos x divided by x to the power 4. Okay, I hope that makes sense. So these are pretty much all the rules of differentiation. If you know and understand these three rules, you can differentiate any function, as I shall demonstrate. So for example, here I have, this is a quotient rule, so it's the derivative. So f dash of x, the derivative, is x squared sine 3x dash multiplied by x cubed plus 1 squared minus x squared sine 3x multiplied by x cubed plus 1 squared dash. So I'm using the quotient rule first. And divided by x cubed plus 1 to the power 4. Now, I don't want to carry all this stuff with me, so I'm going to do this part separately. So I'm going to write out this bit. So x squared sine 3x dash. So that's going to be a product rule here. x squared dash multiplied by sine 3x plus x squared multiplied by sine 3x dash. A derivative of x squared is 2x sine 3x plus x squared. Now, the derivative of sine 3x. Remember, sine f dash is cos f multiplied by f dash. So sine 3x is cos 3x multiplied by 3x dash. So this is 3 cos 3x because the derivative of 3x is just 3. And there's a multiplied by 3 cos 3x. Okay, we've dealt with this bit. Now we need to deal with this bit. So let's take a different color, green. X cubed plus 1 squared dash. Now I could write x cubed plus 1 times x cubed plus 1 and use the product rule. But I'm going to use the chain rule here. And this, I'm going to treat it as f squared. And f squared is 2f multiplied by f dash. So it's going to be 2x cubed plus 1 multiplied by x cubed plus 1 dash, which is 2x cubed plus 1 multiplied by 3x squared, which is 6x squared, open bracket, x cubed plus 1. All right. And I use these results and I put them all back in to get the final answer, which I do not need to simplify because it will take more time to simplify than actually solve it. So that's going to be 2x sine 3x plus x squared 3 cos 3x bracket x cubed plus 1 squared minus x squared sine 3x multiplied by 6x squared multiplied by x cubed plus 1. Right. Okay, you could simplify it a little bit. You could simplify. Well, no, it's not necessary. You don't have to do it. Yeah, that's the answer. That's it. So you can see that I've used the chain rule, the product rule, and the quotient rule all in one question. And this could have the complexity can be it can be a very complex thing. Okay, a very similar question here. So I've got 3 very similar questions just to show you how I deal with them. So g dash of x. Now this is a quotient rule, so I need to differentiate that. So e to x 5x minus 3 dash multiplied by square root of 4x squared plus 1 minus e to the power 2x 5x minus 3 multiplied by the derivative, so 4x squared plus 1 derivative all over 4x squared plus 1 square root squared. Okay. Once again, I'm going to simplify this bit separately. So e to the 2x 5x minus 3 dash is e to the power 2x dash multiplied by 5x minus 3 plus e to the power 2x multiplied by 5x minus 3 dash. And recall that e to the power f dash is e to the power f dash. And that means that e to the power 2x dash is e to the power 2x multiplied by 2, because the derivative of 2x, which is 2e to the power 2x. And yeah, so that's going to be 2e to the power 2x, open bracket, 5x minus 3, plus, well, that's 5, as a matter of fact. So the derivative of 5x minus 3 is just 5, so it's plus 5e to the power 2x. Now, it would be very silly not to open the brackets here, because it's going to be, well, would it? Well, yeah, let's open the brackets. It's going to be 10e to x. If the power is not x, is it guaranteed to use the chain rule instead of the basic rules? Well, use the chain rule. Look, I'll say a few words about the chain rule. But yes, you can always use, so whatever that is, so for example, e to the power square root of x squared minus 7x. So whatever that is, it will always be e to the power square root x minus 7x multiplied by the derivative of whatever that is, 7x. That's the idea. So if the power is not x, you always use. But even if the power is x, you can still use that rule. It's e to the power x multiplied by x dash, but x dash is 1, is equal to 1, so it's just e to the power x. So yeah, it works either way. How do we know, well, we know how much to simplify? Uh, the question usually specifies whether you need to simplify or not. A question like that, uh, a question like that would normally not need simplification unless they're being very cruel to you. So yeah. And okay, so 10e to x times x minus 6e to the power 2x plus 5e to the power 2x, which is 10x e to x minus e to x, which can be written as e to the power 2x, open bracket, 10x minus 1. Okay, that looks slightly better. Right, finally, I got this bit. Let's use purple color for this. So how do we deal with that? So square root of 4x squared plus 1, and I want to find the derivative. So to find the derivative, well, first of all, I treat it as 4x squared plus 1 to the power 1/2, and then I use the rule that f to the power n dash is nf to the power n minus 1 times f dash. So that's going to be 1/2 multiplied by 4x squared plus 1 to the power minus 1/2 multiplied by 4x squared plus 1 dash. And therefore, so that's 8x divided by 2. So that's 1/2 multiplied by 4x squared plus 1 to the power minus 1/2 multiplied by 8x. So that's 4x, open bracket, 4x squared plus 1 to the power minus 1/2. And I'm going to use that. I'm going to use that and that to fill in the gaps. So that is e to the power 2x, 10x minus 1, square root of 4x squared plus 1, minus e to the power 2x, 5x minus 3, multiplied by 4x. And this is just 1 over square root of 4x squared plus 1, all over 4x squared plus 1, because this square root goes away. And we're going to keep it that way. Could you show that what the derivative of a to the power x squared would be? I could. I hope it's not in the assignment. A to the power x squared. Well, first of all, you need to know what a derivative of x is. Well, a to the power of x um, is a to the power x multiplied by ln a. That's the rule. That's from the table. So if you rewrite that rule as a to the power f, and you can do this trick with any standard differentiation. AF is going to be a to the power f multiplied by ln a multiplied by f dash. Okay, let's take any exotic differentiation. So derivatives, table of derivatives. Derivatives. Let's take some exotic derivative. Yeah, come on. Okay. You don't have to. You don't have to know it, but yeah. So this is a sort of exotic derivative, right? So it says that the sec x dash is sec x tan x. Now replace x with an f. So sec f dash is sec f tan f dash. So literally, I can differentiate anything I want. So sec instead of x, sec 3e 3x plus sine x. Right? So any crazy derivative, I can do it. I can just do sec 3e 3x plus sine x um multiplied by tan 3e 3x plus sine x multiplied by 3e 3x plus sine x dash. And then I deal with this, but this is simpler to deal with. So here I use this rule again. Um, so what I want to do is, yeah. So if you want, if you want to do a x squared, if you want to apply this rule, this is simply going to be a x squared multiplied by ln a multiplied by x squared dash, which is just 2x. So the answer is going to be 2x a x squared multiplied by ln a. I hope that makes sense. Okay. Ln a, natural logarithm. Natural ln a is logarithm of a base e. Look it up, please. If you're not familiar with it, do look it up. You do study it in year 12. You're supposed to study it in year 12, maybe just not yet. Okay. All right, we've done this one. Okay, one more, one more horrible derivative, and then I'll do something else. A to the power x log a. Yeah, that's what I said, no? A to the power x is a to the power x. Oh, log a. It is different. No, it's not log a. Log a would be a mistake. It's not log a. It should be, yeah, log to base e, yeah. You could write it as a to the power x multiplied by log e a, like this. People don't normally write it like this. Okay, let's do this. So now we have, well, same idea. We have, we need to differentiate h of x. I'm going to attempt to do it straight away. So I want to differentiate that bit. So that's going to be 2x plus 4. That's the derivative of that, multiplied by cos 2x plus x squared plus 4x, multiplied by the derivative of cos. The derivative of cos is minus 2 sine 2x. And then I multiply this by 3x minus 1 cubed minus, then I just copy the top, x squared plus 4x multiplied by cos 2x, multiplied by, and then derivative of the bottom, that's going to be 3x minus 1 squared. So I applied the power rule, and then I multiply by the derivative of 3x minus 1, so it's just 3. And then I divide everything by 3x minus 1, 6. So you can see I literally just used one line of writing to do the whole thing. So yeah, derivatives are fun. And okay. Next problem is connected rates of change. So here is where you need to use the chain rule in the form that it is normally written in textbooks. And the chain rule looks like this. Chain is that dy dx can be written as dy du multiplied by du dx. So for this, the volume increases. So here we have volume, which is v. We have radius, which is r. And we have t is time. So we write down the chain rule that dv, the derivative of volume by dt, can be written as dv dr multiplied by dr dt. Okay. And what it says, the volume increases at a rate. So that is the rate of increase of volume. So that's literally dv dt. That's the rate of change of volume. The definition of a derivative is the derivative is the rate of change. Okay, so we use the chain rule here. Now, we need to find the derivative of v. So dv dr. So we just differentiate this. So it's 4 over 3 pi r cubed. The derivative, which is 4/3 pi r cubed derivative. And the derivative of r cubed is simply, so 4/3 pi multiplied by 3r squared. 3 cancels, and it's 4 pi r squared. It's actually the derivative of v is the expression for area, and it's not a coincidence. But all right, so we found dv dr is this expression, so we can plug it in here, and then dr dt. Okay, so dv dt is 4 pi r squared multiplied by dr dt. And what's this saying? So the rate at which the radius is increasing. So what's going on? So a balloon is a sphere, and air is being pumped in. Air pumped in. and the volume is increasing. And the rate at which the volume is increasing, the dV dt, is 20 centimeters cubed per second. We want to find at what rate is the radius increasing. So dr dt is question mark. That's what we need, dr dt. And that's what we have here, dr dt. So dr dt is equal to 1 over 4 pi r squared multiplied by dv dt. And we know that the radius is 10. Radius is 10, and dv dt, we already know it's 20 centimeters cubed per second. So 1 divided by 4 pi times 10 times 20 centimeters cubed per second. This is centimeters squared. And so that is, well, something. 20 divided by 4 divided by pi divided by 100. 0.0159 centimeters per second. So that's the rate at which the radius is increasing. So every second, the radius increases by 0.0159 centimeters. That's what it means. So dr, that's what it says when we mean that dr dt is that. That's what we mean. That's what the derivative is. Lovely. And that's called connected rates of change. So, and it is also in your A-level syllabus. So if you haven't studied it yet, you can always open your textbook and have a look at it. Okay. Maximum and minimum on a closed interval. Now, so here we start using derivatives for practical applications. Well, I don't know how much practical it is finding a maximum and minimum of a function, but that's the idea. We have a function has a minimum or a maximum. Let's imagine a function on an interval. Right, so the function can go like this. So let's say we have a function on an interval from a to b. So that's f of x. So f of x is a continuous function on the interval ab. And we need to find the minimum and the maximum. And you can clearly see. So what's happening here is that we have 4 potential minimum or maximum points. So we have the ends, f of a, so that's f of a. This is f of b. And also these points. These points are called critical points. Critical points. They're minimums and maximums. But a maximum isn't necessarily bigger than fb. So you can see that the maximum value of the function is fb, not the value at the critical point. So the minimum or maximum of a function on an interval, min or max of f on AB can occur at critical points or at the ends of the interval. And that's Yeah, so we need to find the critical points. The critical point is where the derivative of the function is 0. F dash of x is 0. And that's what we do. So yeah, we find the value of the function on the interval, on the ends of the interval, and we find the value of the function of the critical points. So step 1, find critical points. To find the critical points, we do the derivative of x, and that's 3x squared minus 12x plus 9 equals 0. We find where the derivative is 0. We can divide the whole thing by 3. So x squared minus 4x plus 3 equals 0. So x equals 1 and x equals 3. So these are the critical points. Step 2, find the value of f at critical points and the ends of the interval. So we need to find f of 0, f of 1, f of 3, and f of 5. F of 5. So f of 0, we just literally substitute 0, is 4. F of 1 is 1 minus 6 minus 5. Minus 5 plus 9 is 4, 8. F of 3, so substitute 3, 27 minus 6 times 9, 54, plus 9 times 27, plus 4. Oh, wow, that's just 4. And f of 5, that's 125 minus 6 times 25, which is 150, plus 29 times 5, so it's 45, plus 4, and that is 24. And then we choose the minimum value. Min value is 4. Max value is 24. Why did we skip 2? Well, 2 is not a critical point and not an end of the interval. But critical points. So ends of the interval, that's 0 and 5. And the critical points are 1 and 3. Right? Does that answer your question? Okay. Once again, here we have the interval from 0 to 10. And we have a function, so we find the critical points. Critical. So g dash x, so we use the product rule here. So that's going to be x dash multiplied by square root of 10 minus x plus x multiplied by square root, well, the derivative of that, so it's 1/2 10 minus x to the power minus a half multiplied by minus 1. So I use the chain rule here. And this is just 1, so that's equal to 0. So that's square root of 10 minus x minus x divided by 2 square root of 10 minus x equals 0. Square root of 10 minus x equals x divided by 2 square root of 10 minus x. Multiply both sides by square root of 10 by 2 square root of 10 minus x. So 2 10 minus x is equal to x. 20 minus 2x equals x. X is 20/3. So that's the only critical point. So then we just need to find f of 0, f of 20/3, and f of 10. So f of 0 is 0, easy. F of 20 thirds, so that's 20 thirds multiplied by square root of 10 minus 20 thirds. So that's 30 minus 20. 20 thirds multiplied by square root of 10 thirds, which is 20 square root of 10 divided by 3 square root of 3. Okay, well, it's more than 0. What can I say? And f of 10, so that's 10 multiplied by 10 minus 10, which is 0. Okay, that min value is 0. Max value is 20 root 30 over 9. I can just simplify it. 12.17. Is that? Yeah. Yeah, I can multiply top and bottom by root 3. So that's 20 root 30 over 9. Okay. Now, derivatives are used in optimization all the time. In economics, for example, where a very common thing that you do is, well, for example, optimization. So my favorite example in optimization is in economics. So imagine that you are selling, if you're selling bread, you are selling bread. And it turns out that this is your price and this is the quantity. And imagine that if the higher the price, the less bread you will sell. So if your price of a loaf of bread is £10, you'll probably sell nothing. And if you can make 100 loaves of bread, then if your price is £0, you will sell 100 loaves of bread because that's how much you can make. That's how much you can bake. And as you increase the price, you will sell less. So you can write down a function. You can say that the quantity of bread sold is a linear function. So 100 minus 10 times the price. Yeah, because so if your price is £3 for a loaf of bread, okay, quite an expensive loaf, but that means you'll sell 70 loaves of bread. If the price is £6, it's a very big loaf. Okay, it's a very big loaf of bread. Your price is £6, then you'll probably sell 40 loaves, etc. Right? In your artisan bakery. Look, okay, so sorry for the random example, but what about your revenue? Your not your profit, obviously, your revenue, because your revenue is the how much money you make is how much you sell multiplied by how much multiplied by the price. So revenue is 100 minus 10p multiplied by p, which is 100p minus 10p squared. And if you want to max, and you can see that this is a quadratic function. So if your price is 0, your revenue will be 0. You make 0 money if your price of the loaf of bread is 0. And if your price is 10, you also make 0 because you sell exactly 0 loaves of bread. And somewhere in between, there's an optimum point which maximizes your profit. So maximum revenue, not profit, maximum revenue. Because profit and revenue are different things, but that doesn't really matter today. So this is your revenue. And that's what you're looking for. That you're looking for the point where the derivative dr dp is 0. So you take your revenue equals 100p minus 10p squared, p squared, and you find the derivative of revenue by price, and that gives you 100 minus 20p, and we need to find where it's equal to 0 because that's the maximum value. And then 100 equals 20p. P is 5. So your price has to be 5 in order to reach maximal revenue. And this is used a lot. So this is an economics example. So if you go to study economics, that's the kind of stuff that you will be doing. But it also involves maximization. So any problem on maximization or minimization is called an optimization problem, which is what we're doing. So optimization for geometry. So you have a rectangular poster which has to have an area of 600 square centimeters. Okay. Let's let the length of the poster be x and the width y. So we know that x multiplied by y must equal to 600. Okay. But we have to have margins. The top and bottom margins must be 4 centimeters. So you can only print on that area, of course, because when you have a poster, you have to leave some space on the margins. So this is 4 centimeters. 4 centimeters. And then here we have 2 centimeters on the edges. 2 centimeters. So that means that this length is actually y minus 8. And this length is x minus 4. So the printed area A is x minus 4 multiplied by y minus 8. From here, we can express y. We can express y as 600 divided by x. And we can sub that into here. So A is x minus 4 multiplied by 600 over x minus 8. Let's open the bracket. At brackets, A is equal to 600 minus 8x minus 2,400 over x plus 4 times 8, 32. Okay, so printed area is 632 minus 8x minus 2,400 x to the power minus 1. To find the maximum, to maximize the printed area, area is maximum when the derivative is 0. So we find the derivative of that. So a dash is 0 minus 8. Now, the derivative of this is going to be plus 2,400 x to the power minus 2, because that's how derivatives work. And then we can, and that's equal to 0. So we have 2,400 x to the power minus 2 is 8. So 2,400 is equal to 8x squared. X squared is 300. X is square root of 300, which is approximately 17.3. Square root of 300 is 17.3, yes, centimeters. Right. And Y is 600 divided by X, which is 600 divided by square root of 3 times 100 times 10, which is 60 divided by root 3, which is 60 root 3 over 3, which is 20 root 3, 20 root 3, which is approximately 34.6 centimeters. 20 root 3 indeed is 34.6. I was correct. Okay, kind of pleased with myself. Good. Right, so that's the dimensions. That's the size of the printed area that maximizes. So that's the size of the poster that maximizes the printed area. Okay. Now, cost minimization. This is also a very, very important application of derivatives. A company designs a cylindrical container with fixed volume 500 centimeters cubed. So this is cylindrical container, and the volume is 500 centimeters cubed. The top and bottom, so the top and bottom, are made of a material costing 4 times as much. So the price of top and bottom is 4 times as much as the material used for the side. Find the radius and height of the cylinder that minimize the total material cost. Okay. So first of all, we have the radius and we have the height, h. And we know that the volume is pi r squared multiplied by h. Now, the price of the material, so we can assume one p. Well, because the cost doesn't matter. Like, it doesn't matter how much the material costs. Okay, assume top costs 4a per centimeter squared, where a is the price per centimeter, and the side costs a per centimeter squared. Okay. So area of this side is 2 pi r multiplied by h, because if you cut the can, you unwrap it, it's going to be a rectangle of length 2 pi r and height h, and the price is going to be a multiplied by 2 pi r h. The area of the top plus bottom is 2 pi r squared, and the price is 4a multiplied by 2 pi r squared, which is a multiplied by 8 pi r squared. So the total price of the can, of the material for the can is a multiplied by 2 pi r h plus a multiplied by 8 pi r squared. Now, since we know the volume is 500, so from here, we can write that pi r squared h is 500. That means h is 500 divided by pi r squared. And we can substitute that into here. So total price, let's call P. P is A multiplied by 2 pi R multiplied by 500 divided by pi R squared. Pi cancels, R cancels, plus A 8 pi R squared. So P as a function of R. Yes, so for different radius, the price is going to be different. Price depends on the radius. And this is A multiplied by 1,000 divided by R plus A multiplied by 8 pi R squared. Now, the price is minimum when dP dr is 0. So we differentiate that. So P dash, which is equal to A multiplied by 1,000 multiplied by -1 R minus 2 plus A multiplied by 8 pi, because A is a constant, so we just keep it, times 2R, and that must be equal 0. And then I get 16 A pi R is equal to 1,000 A over R squared. A cancels. R cubed is 1,000 divided by 16 pi. So R is approximately cube root of 1,000 divided by 16 pi, which is cube root 1,000 is 16. 2.71 centimeters. And height, we know that height is 500 divided by pi r squared. So it's 500 divided by pi multiplied by 2.71 squared equals 500 divided by pi divided by answer squared, which is 21.7 centimeters. Okay. And that is the dimensions of your can. So if you were making cans, you would probably be looking to minimize the price of the can. 2.71 is the radius and 21.7 centimeters is the height. It's quite a long can, but you can think of like a Coca-Cola can or something. Okay, it could be a minimum or a maximum, but it could be a minimum or a maximum. But if you consider the extreme case, because minimum or maximum could be at the ends of the interval as well. And if you find the interval of the ends of the interval, radius is 0. Well, that doesn't make any sense. Radius can't be 0, just as well as h can't be 0. So it kind of from the context, but yes, you can do the second derivative and find that. But normally in an optimization problem, you don't need to prove that it's a minimum or maximum because there's only one possibility. Okay, so if you're confused, if you don't know, then you can find the second derivative and verify. But normally, just there's only one option. Yeah. But yes, that's apologies. It's not well, yeah, it's obvious from the context. So I'll be finishing here. Yes, I'm really not feeling well, so I want to finish a little bit early today. And this is the last webinar of 2025. So the next time I see you in January. So have a lovely holidays, have lovely holidays and a lovely new year. And I'll see you all in January. Okay. There was a question. Tell me with them mock tomorrow. Well, good luck with good luck with your mock. What can I say? Sorry. All right. Okay. See you all. See you all.